Hello everyone and welcome back. Today we're going to continue our explorations of foundations of mathematics and explore how to solve absolute value equations and absolute value inequalities. So before we dive into the actual solutions of equations and inequalities with absolute values, let's just make sure we understand how to find the absolute value of a variety of different types of numbers. For example, if somebody says the absolute value of 0, you would say that's equal to 0. In some sense, you can say that 0 does not have any distance from itself. Similarly, the absolute value of negative 3 will be equal to 3, which can be interpreted as, okay, you are 3 units away from 0 on the real line. Similarly, the absolute value of 5 will be equal to 5 because it's 5 units to the right of 0. And you don't have to just analyze numbers. For example, if x belongs to reals, it could either be positive, negative, or 0. You could also do complex numbers as well. For example, if somebody says the absolute value of 3 minus 2i, keep in mind 3 minus 2i is similar to the point 3 comma negative 2 in the R2 plane. So the distance from 3 negative 2 to 0 0 would be found by doing the square root of the real and imaginary parts squared for this particular complex number. So that's going to be equal to 3 squared plus minus 2 squared, which is going to be the square root of 9 plus 4, which is just going to be equal to the square root of 13. And you would apply this type of procedure for any x in the set of complex numbers. So that's how you would find the absolute value of any complex number for which you're interested in. So now what we're going to do is we're going to be working backwards, i.e. I'm going to tell you what the absolute value is, and you're going to tell me which number it is, has that particular absolute value. So let's start off with some very basic examples, and let's assume the directions are solve for all x and r, all real numbers that satisfy these particular relations. So first, if the absolute value of x is equal to 3, what are my solutions to this particular equation? So x obviously could be equal to 3, or x could be equal to minus 3. Second, if the absolute value of x is equal to 0, there's only one number whose distance is 0 from 0, and that's obviously just going to be equal to 0. And 3, the absolute value of x is equal to minus 7, whose absolute value is negative 7, in particular a negative number. In particular, there is no x in the set of reals that makes this true, and that's because the absolute value of x is greater than or equal to 0 for all x in the set of reals. And also, it's not just for all x in R, but it's also no x in C as well, because this statement is also true for all x in C, right? Because if we were to extend, for example, this equation to C, you can say, oh, well, we could also say that x is equal to 3i minus 3i, and actually infinitely many others all satisfy. But regardless of the type of number that you're working with, the absolute value is always going to be non-negative. So that's a very important thing to keep in the back of your mind when we are solving these types of equations and also inequalities. Right? So let's just review just one basic thing associated to absolute value functions. So let's assume that f maps some value x in R to some value y in the set of R. So R is our domain and R is also our codomain. And let's assume we define this relation via the function f of x is equal to the absolute value of x. So what does the graph of this particular relation look like? Well, you probably already do know what this looks like. This should look like a V, right? So this is a V graph, as some people will talk about it. And obviously, the domain for this particular relation R is going to be the set of all real numbers, or minus infinity to infinity, and the range for this particular relation is 0 to infinity, because, keep in mind, the absolute value of a number is always non-negative, in particular for all real values x. Right? So now that we know just some basic things about absolute values and also know how to solve some basic absolute value equations, let's make these equations a little bit more complex. All right, so let's assume that again we're going to be solving for all x in the set of real numbers. So first equation, Let's assume that we have the absolute value of 3x minus 2 is equal to 7. So we can view this object as just another real number, say y, because if 3x and 2 are all real numbers, then that is also a real number as well. So we can say, okay, well, this is the same as the absolute value of y is equal to 7. So we already know how to solve this particular type of equation because that's going to be either y is equal to 7 or y is equal to minus 7. But keep in mind we did not start off with any y's in our equation, so we would have to switch back into our original variable. So that's going to be either 3x minus 2 is equal to 7 or 3x minus 2 is equal to minus 7, which are two different linear equations. So we're going to add 2 to both sides for both, so we're going to have 3x is equal to 9, or 3x is equal to minus 5, which means that x is equal to 3, or x is equal to minus 5/3. So those are our two solutions for this particular absolute value equation that we started with. So let's just work through a couple more examples just for practice. The absolute value of 5x plus 7 is equal to 8. So we're going to break this down. So either 5x plus 7 is equal to 8, or 5x plus 7 is equal to minus 8. Subtract 7 from both sides, so we have 5x is equal to 1, or 5x is equal to minus 15, which means that x is equal to 1/5, or x is equal to minus 3. And you should be able to take both of these and substitute them back in and verify that both of them actually do work. And I definitely recommend this if you're new to solving any types of equations. So the absolute value of 3x plus 8 is equal to 0. Keep in mind there's only one way that the absolute value of something is equal to 0, and that's if the interior statement is equal to 0. So that's a basic linear equation. So x is going to be equal to negative 8/3, and that's going to be our only solution. So we have two solutions potentially, one solution potentially, and let's look at another solution. The absolute value of 8x plus 12 is equal to minus 7. And you can say, okay, well, 8x plus 12 is equal to 7, or 8x plus 12 is equal to minus 7. But that's not true because the absolute value is always greater than or equal to 0 for all inputs that are real. So it cannot be equal to a negative number, so don't even try to solve this. So here we say that x is not a real number. Moreover, we can also say that there's also no complex number that satisfies this. Therefore, this absolute value equation has no solution anywhere, right? So that's very important to note. Also, a couple little identities that you should keep in mind when you're doing some absolute value equations. The first one is that the absolute value of x minus y is generally not equal to the absolute value of x plus y. And moreover, a specific example, if you have, for example, negative 3 times the absolute value of x minus 2, this is not necessarily equal to the absolute value of minus 3x plus 6, i.e. you cannot distribute into absolute values. So this is not a parenthesis, so you cannot do such things. All right. So with that in mind, let's look at another example just for practice. The absolute value of minus 3x plus 6. So what exactly is this equal to? So if I don't want to deal with this expression, I can probably factor out a minus 3 out of the interior, giving us x minus 2. And what I can do, because there's one theorem that is true for absolute values, and that's the absolute value of x times y is actually equal to the absolute value of x times the absolute value of y. That's a fun exercise to prove. So that means this is actually equal to the absolute value of minus 3 times the absolute value of x minus 2, which is the same thing as 3 times x minus 2. So notice that this thing is actually equal to the opposite of that coefficient, which is actually, generally speaking, quite different, right? So this is just some important things that you definitely should know when solving basic absolute value equations. Let's look at a slightly more complicated variation of absolute value equations, where we have the absolute value of some function of x on the left and some absolute value of function of x on the right. So you can technically represent this. Okay, we have the absolute value of f of x is equal to the absolute value of g of x, with nothing on the outside of these absolute values. Right, so what exactly do we have going on here? So if you remember, the graph of absolute value relations, for example, we can say that that's y1 and that this is y2. They're both v relations in terms of their graphs. So what are the possible cases of solutions? Because we've looked at a few cases where we have one solution, two solution, or no solutions, right, for the previous equation. So what are the possible cases here? Right, so let's actually take into consideration a few of them. So one equation is where you have, for example, 1v here, and you could also have 1v here, for which these do not ever cross. So this would be, for example, a no solution variety. Another situation that you could encounter is where you have, for example, 1v here, and you could also have, for example, 1v here, for which they cross at, for example, 1 x value there. So in this particular case, you would have one solution. You could also have two solutions. Maybe you can sort of illustrate your own example here. You could have, for example, 1v here, and you could also have, let's say, 1v here, where you have, for example, 1x here, and then another x there. So in this case, we would have two solutions. And you could actually have a few strange setups. For example, let's assume you have 1v here, and let's assume that you have 1v here, right? So notice that there's actually infinitely many solutions, right? So infinitely many solutions on this particular region. So infinitely many solutions to this particular system or set of equations, where all x values within this interval, inclusive of those boundaries, would be included because that's where these two v's overcross or crossover. So no solution, one solution, two solution, and infinitely many solutions, and there's a variety of different structures for infinitely many. For example, a closed interval, open interval on both sides, or something along the sorts, right? So what type of situation do we have when we have 3x minus 2 is equal to the absolute value of 2x minus 5? Exactly how many solutions are there to this? So one can show, and I'm not going to go through this proof, but it's actually not too hard to show using the methods that we discussed previously. We can say that 3x minus 2 is equal to the right-hand side without the absolute values, or the left-hand side, 3x minus 2, is equal to the opposite of the right-hand side without, again, the absolute values. Right? That's not too hard to show why that is the case. So obviously we have two equations, right? So let us see if we can sort of solve this out and see what we have. So what I'm going to do is I'm going to isolate this. I'm going to bring our 2x over and our minus 2 over. So I'm going to have x is equal to 3 as our negative 3 as our first solution. Or what we're going to have, so let's distribute that negative, so 3x minus 2 equals minus 2x plus 5, so bring our minus 2x over, our minus 2 over. So that's going to give us 5x is equal to 7. So that means x is going to be equal to 7/5, right? So we have how many solutions here? So that means we're going to have two solutions, right? So our solution set here is going to be equal to minus 3 and 7/5 as our solution set. Right? So this is one of those cases where you have, for example, something along this line in terms of graphs. Okay, let's just do one example just for fun. So example 2. The absolute value of 5x minus 3 is equal to the absolute value of 5x plus 2. You might want to guess, just by looking at these linear relations on the inside, how many solutions will we have? So what we're going to do is we're going to have 5x minus 3 equals the right-hand side, or 5x minus 3 is equal to the opposite of the right-hand side. So, canceling out, we're going to have minus 3 is equal to 2, which is not possible. So this equation gives us nothing at all. And over here, we're going to have 10x is equal to 1, or x is equal to 1/10. And we just have one solution. And you can plug this into our original curve and make sure that that does actually work, right? So one solution, two solutions. Let's actually look at another equation to sort of see, is it possible that we can generate a strange solution? Maybe, maybe not. We'll see. So example 3. Let's assume we have the absolute value of x minus 2 equals negative absolute value of x plus 2. So this is a little bit more complicated, right? So let's sort of treat it like we did before, but very, very carefully. So x minus 2 is going to be equal to the right-hand side, or x minus 2 is equal to the opposite of the right-hand side, right? So obviously we're going to have x is equal to the absolute value of x here. There's infinitely many solutions to this because we know that this is true for all x greater than or equal to 0. In particular, x is equal to 0 is one of them. And what do we have going on over here? So if we have this expression, for example, if we subtract 2 from both sides of this, we're going to have x minus 4 is equal to the negative absolute value of x. So the absolute value of x is equal to 4 minus x, which is, again, another absolute value equation. So either x is equal to 4 minus x, or x is equal to x minus 4, the opposite. Notice that this equation is going to give us 0 is equal to minus 4, which is useless, so that's not going to help us. And over here, we're going to have 2x is equal to 4, which means that x is equal to 2 is going to be our solution. So notice that x is equal to 2 is a solution, and also we have this true for all x greater than 0. But also we have a couple contradictions here and there where it's, for example, always true, not always true, never true, and so on. For example, 0 is never equal to minus 4. We have a point, we have an interval. So exactly how do we deal with this? So every time you have an algebraic equation where you know how to solve, I'm not saying that there's not a way to solve it. In particular, there is some ways to algebraically figure this out by hand, but sometimes graphical situations are the best way to deal with it. Okay, so what I recommend when you don't know how to deal with it, for example, the absolute value of x minus 2 is equal to the absolute value of x plus 2, is do graphical methods for this because they will never fail you as long as your graphs are decent enough. So what we're going to do is we're going to define the left-hand side to be a function of x, and we're going to be defining the right-hand side as a function of x. As long as you can graph both of them to reasonable accuracies, you should be able to solve this with no issues. So we're going to have f of x is equal to the absolute value of x minus 2, which we should know is just an absolute value graph which is shifted to the right 2 units, right? And it has a y-intercept of 0, 2 as well, right? X-axis, y-axis. And if we have g of x is equal to negative absolute value of x plus 2, we already know that that is going to be upside down, shifted up 2 units. So this is going to be the graph of that, right? So if we overlap these two curves on top of each other, keep in mind, this is f in disguise. Notice that these two curves overlap on this interval here. Right? So from graphical analysis, we see that the solution interval is the interval 0 to 2. So every number between 0 and 2, inclusive of those boundaries, will work. And we can also write this in expanded form, in particular all x and r that satisfy 0 less than or equal to x less than or equal to 2. So keep in mind, just because there is an algebraic equation does not necessarily mean that there is an algebraically way to solve it. Actually, with even a finite amount of functions, there always exists some algebraic function that you cannot solve with the tools for which you have created, which is a very important result, which we'll get to later. But for now, just keep in mind, graphs are always a good solution as long as you have the tools and software available to graph them up to any amount of precision. Now that we know how to solve absolute value equations involving one or more absolute value expressions of linear functions, now what I want to do is just take a brief look at how to solve absolute value inequalities. So let's assume that we have an absolute value relation that is always above the x-axis. And we're like, okay, if this is our function, say f of x, where x is on the horizontal axis as usual, when is this graph above the x-axis, i.e. when is this greater than or equal to 0? We can either mandate it's strictly positive or at least never negative. And we clearly see that this is always greater than or equal to 0. Agreed? So if we look at another absolute value relation, for example, this. So when is this particular relation above the x-axis? Where it's going to be above the x-axis on this particular interval. Let's not shade the curve, but rather shape the real axis for which the solutions are going to be located, right? So for example, from minus infinity to a and from b to infinity. So that's when, for example, this particular relation, let's call it g, for example, this is when g of x is strictly greater than 0. So it's sometimes, solving that particular relation. And for example, if we had another type of relation, for example, this one, let's assume its vertex is there, then obviously it's, there's one point for which this inequality is satisfied. So again, that would be a sometimes situation. And let's assume that we have another relation, for example, something like this. And again, we want to know when this is greater than or equal to 0. And in this case, it will be never. That case, right? So we have at least 4 different cases for solutions to absolute value linear inequalities. So let's look at a couple algebraic examples to start to see if we can figure out which is which. So first example, let's assume that we have the absolute value of 5x minus 2 is greater than or equal to minus 3. So we know that the absolute value of 5x minus 2 is always greater than or equal to 0, and we know that 0 is greater than minus 3. So since 0 is greater than minus 3 and absolute value is always greater than or equal to 0, that means absolute value of 5x minus 2 is always greater than negative 3. So that means the solution is all real numbers. So all real numbers would be the solution to this particular absolute value equation. All right, so let's see if we can solve a less trivial example. So for example, when is the absolute value of 5x minus 2 greater than or equal to 0? Well, we already know that absolute values are always non-negative, so again, this is all real numbers, so that's not too bad. So when is the absolute value of 5x minus 2 strictly bigger than 0? Well, this is going to be true for all real numbers except for when that absolute value is equal to 0, which occurs when x is equal to 2/5, right? So when that is equal to 2/5, it's equal to 0, right? Because we're like, okay, well, we have 5x minus 2 is equal to 0. Well, that means that 5x minus 2 is equal to 0, which means that x is equal to 2/5. So that's the value that produces 0, and that's the value that we do not want. Okay, so let's answer a little bit more of an interesting question. The absolute value of 5x minus 2 is greater than 3. All right, so this is where we introduce, the same algebraic strategy as we did for just equations. So we're going to split this up into 2 linear inequalities. So we're going to have that 5x minus 2 must be greater than 3, or 5x minus 2. So 5x minus 2 is less than negative 3. So we multiply the right-hand side by negative 1, and in some sense that's what flips that sign around. So we're going to add 2, so we're going to have that 5x must be greater than 5, or 5x must be less than minus 1, which means that x must be greater than 5 over 5, which we know is going to be 1. Or when x is less than negative 1 over 5. Right? So if we look at a number line and plot, for example, negative 1/5 there, and let's plot 1 here. So x is greater than 1, that's this right-hand part. X is less than negative 1 over 5, that's that part there. So this is where it satisfies the inequality. So that means x must belong to the interval minus infinity to negative 1/5 union 1 to positive infinity. Right? So that's pretty much what's going on here for this particular linear inequality. Right? So if we look at the graph of what's going on here, so what exactly do we have, right? So let's bring it back that example and sort of get a graphical understanding of what we're looking at. Let's assume that we call this function right here f of x. So what does this function look like? So the absolute value of 5x minus 2. So what I'm going to do is I'm going to factor out a positive 5 out of this. So I'm going to have 5 times the absolute value of x minus 2/5. And keep in mind, if you factor out a negative 5, it still will come out as positive 5 on the outside. So what this is a v shifted to the right 2/5 units. So 2/5 units, let's pretend, is somewhere over there. And it's going to be narrowed up a bit because of that 5, but let's sort of scale out this so it doesn't look too strange. All right, so that's the graph of our v. And what we're doing is we're saying, okay, well, on the interval minus 1/5 and 1, this curve is above 3, right? So this should be where 3 is located, and it's above this y is equal to 3 line, starting at those points, right? So that's when this curve is above that purple line, right? So any x in this interval will make that true. Okay, so that's how we can solve at least simple linear inequalities. And obviously, if it gets super more complicated and you don't know the algebraic trickery for it, you can always go to graphs. So the last thing that I want to talk about today is instead of solving equations and inequalities over the set of real numbers, we don't actually have to solve it over the real numbers, but we can solve these absolute value equations over the set of complex numbers instead. And this is actually a little bit interesting and has quite a few applications. So the absolute value of z is equal to 0. Again, there's only one complex number whose absolute value is 0, and that's going to be the absolute, the number z is equal to 0, which can also be written as 0 plus 0i. And 2, if we have the absolute value of z is equal to minus 3, then we already know that there is no complex number whose absolute value can be negative, because we know, again, the absolute value of z is always going to be a real number that's always non-negative, and that's going to be true for all z that belongs to the set of complex numbers. Right? So, for example, if somebody says the absolute value of z is equal to 5 plus 2i, again, this does not belong to the set of reals. Therefore, there is no complex number z whose absolute value will be equal to 5 plus 2i. Right? So what if I were to put a real number as the output of that absolute value? So this is where it gets fun. So the absolute value of z is equal to 1. What values of z, where z is complex, will make this true? Okay, so if we think about this from the graphical perspective, right, let's put, for example, the real part of z on the horizontal and the imaginary part of z on the vertical. We know that 1 and minus 1 will satisfy this, right? That's positive 1 and negative 1. And we also know that if we take the absolute value of I and minus I, the absolute value of those will also be 1 as well. But are there any others? Well, if you sort of think about what absolute value means, it just means the distance to the origin. So obviously these points satisfy the distance being 1, but there's actually infinitely many more. In particular, if you take any point on this circle of radius 1, as long as this distance is 1, all of these points are going to have an absolute value of 1, right? So for example, if we take the point square root of 2 over 2 plus the square root of 2 over 2i, and we take the absolute value of this, what will we get? So the absolute value of the square root of 2 over 2 plus the square root of 2 over 2i will be equal to the square root of the square root of 2 over 2, the real part squared, plus the imaginary part square root of 2 over 2 squared, and that's going to be equal to the square root of 2 over 4 plus 2 over 4, which is the root of 4 over 4, which is the square root of 1, which we know is going to be 1. Therefore, the square root of 2 over 2 plus the square root of 2 over 2i is a solution to that absolute value equation. So how can we write this solution set, i.e. this circle relation, in a nice form to advertise to our audience? So if z is equal to x plus iy, and we're interested in the set of all z such that the absolute value of z is equal to 1, then the solution set, which I'm just going to abbreviate by S, is going to be the set of all x plus iy, the set of all our z's, such that x squared plus y squared is equal to 1. Right? So it's all points, it's all complex numbers whose real part squared plus imaginary part squared is equal to 1, which is the set of all points similar in R2 that fall in that unit circle. Okay? So let's make this just a tad bit complicated, because now we have some idea of what we're looking at here. So suppose we have the absolute value of z plus 2 minus 5i is equal to 1. Right? Now, if you don't have a geometric sense of what's going on here, you might even want to try to solve this algebraically. So we're like, okay, well, z plus 2 minus 5i will be equal to 1, or z plus 2 minus 5i will be equal to minus 1. So you're going to have that, okay, x plus iy will be equal to minus 1 plus 5i, or x plus iy is going to be equal to minus 3 plus 5i, which means that we have that xy will be equal to minus 1, 5, or x comma y will be equal to minus 3, 5. Right? So notice that we do have some similarity between these 2 points, in particular y is equal to 5, right? But we don't really have any notion of what's going on for x, right? But because we have a range of x, in particular from minus 1 to minus 3. So if we know that the solutions of absolute value equations for complex numbers all form a circle in R2 in terms of the real and imaginary parts, then what we have here is the side of a circle at least, right? Because if we plot this, we're going to have minus 1, minus 2, minus 3, 1, 2, 3, 4, and 5 over here. Let's draw a few points more here. So we're going to have minus 1, 5, which is located here, and then minus 3, 5, which is located here. So these are endpoints of a circle. So if these are endpoints of the circle, that means this must be the center of the circle, which is located at minus 2 comma 5, which if you look at the original equation, which is the absolute value of z plus 2 minus 5i is equal to 1, it's practically the opposite signs of those particular values, right? So obviously if we go to the left 1, we can obviously go up 1 and also down 1, and that's going to form where all of our solutions are going to be located. Right? So this is just going to be a circle centered at xy is equal to minus 2, 5, with again a radius of 1. And we got that radius of 1 from these two endpoints that are generated here. Okay, so let's write this in set form at least. So if you remember the equation of a circle, and if not, that's perfectly okay. But it's going to be the set of all complex numbers of the form x plus iy that satisfy x plus 2, the quantity squared, plus y minus 5, the quantity squared, is equal to 1 squared, which you also say is equal to 1. Which is the circle centered at -2, 5, and radius of 1. So that's how you can solve absolute value equations, both over R and over C, and also how to graphically and algebraically solve some algebraic inequalities. Hope you enjoyed this video, and I'll see you in the next one. Take care.